Using verified normals. When working with membranes and nets, AquaSim has always inferred the direction of the normal to point towards the center of all the elements in the group. This has excluded the ability to work with complex shapes, like for example a donut shape. Working with normal. Using verified normals is only supported by the extended membrane component, also called membrane X or MEmX. When working the membrane X elements, you, as the user, has full control of the nodes and the direction of both vertical and horizontal axis, as well as which side is considered the outside or the inside of the element. Visualization. By toggling the Normals toggle on the toolbar, AquaEdit will show the axis of any selected membrane X element. Here we see the blue line, which denotes the outside of the membrane. We chose to represent the outside, as this makes it easier to visually verify the side of the membranes when looking at it. This especially helps with complex closed volumes. In addition, we can see which sides AquaSim will consider as the vertical axis, the red line, and the horizontal axis, the green line. The horizontal side is also denoted by a dotted line. However, it may be hard to see. In cases where a membrane might be laying flat, like a flat bottom of a net, or as a horizontal surface top, the user will have to decide themselves which side they will consider as the vertical and horizontal side. Editing. In this example, we see 4 selected membrane X elements, 3 of which are pointing outwards from the volume. The 4th is pointing inwards, which when using verified normals is wrong. To change the direction, we can either select the element and right-click. Through the membrane submenu, we choose Flip. This will invert the direction of the membrane, making it point outwards to match the others. Note that the other 2 axes were kept the same. The direction up, down, or left, right do not matter. Alternatively, we can choose to set it to point away from the center of the membrane. This works well for traditional nets. This can also be used when selecting all the elements and applied to them all together. Last, we will change to a more complex example for the last method. Here is a rough donut shape. Selecting all membrane X elements reveals the direction of the membrane elements not to be consistent. In this example, it is vital to use verified normal to help AquaSim understand the geometry. By selecting an element that points in the direction we wish to denote outwards of the volume, we can tell every other connected membrane element to align with this direction. By right-clicking and choosing Membrane, Align Membrane Normal, AquaEdit will attempt to make every element in the component point in the direction of the selected element. For this donut shape, this works very well. However, the caveat is that if the geometry has a bend of more than 90 degrees, the algorithm will fail, and you will have to manually flip the elements based on previous described methodology. Enable export of verified normal. After you have ensured that all membranes have their directions set correctly, you must also enable verified normal by going to Export and enable Membrane Volumes Are Verified to indicate to the AquaSim solver that it should accept the normals. If this is not turned on, AquaSim will consider all elements as pointing towards the center of the component, which, in the case of, for example, the donut, would yield a wrong result. Volume calculations in AquaEdit, AquaView. AquaEdit and AquaView now takes advantage of the verified normals to use a new and improved algorithm for calculating the volume of one or more net groups. When right-clicking on a membrane X component in AquaEdit, you get the option Operations, under which you will find Calculate Membrane Volume. For now, you will get the option to choose whether to use verified normal or not. In our test case here, we have a cube measuring 3 by 3 by 3 meters for a total volume of 27 cubic meters. In the middle, a 1 by 1 by 3 meter hole has been created for a total of 3 cubic meters of volume. Using the calculations for verified normal yields, the expected result of 24 cubic meters. If we did not use the verified normal calculations, the volume would be estimated to be 28 cubic meters, as it was not able to tell what the actual geometric volume looked like. Since we are looking at volume calculations, let us also see how the new algorithm deals with holes in the geometry. In older versions of AquaSim, the user had to manually enable volume calculations and tell AquaEdit if the top or the bottom was open. This allowed it to fill the holes so it could consider it as a closed volume. Now, AquaEdit and AquaView will detect the holes and attempt to fill them. In this case, we see that there is a hole on top and also at the bottom. The hole on the top it can fill with no errors, however, it cannot fully generate the geometry at the bottom, and we get a small amount of error as it smooths over the hole. AquaView. Let's have a look at the same calculations in AquaView. Here we have the same model of the 3 by 3 by 3 volume with the hole. Since this was exported with verified normals, AquaView can use the better algorithm. We use tools, calculate volume, and select our component. The expected result of 24 cubic meters is displayed. This example has no movement, so every time step gets the same expected result. Behind the volume, the percentage of the original volume is shown. This will show decreases in volume as it deforms. If we go back to one of the other examples and go to Tools, Calculate Volume again. We choose an example with 2 components. These 2 components are the bottom and top half of a 1 by 1 by 1 cube. We can multi-select these 2. AquaView will then attempt to merge the geometry and consider it as a single closed volume. We get the expected result of 1 cubic meter. Thank you for listening, and visit our website aquasim.no for more information and tutorials.